I think a great way to start is to just review the, so I call them conceptual frameworks, but the technical term is like the models. Like, what are the things that we studied? And how do we understand them all? And how do they work together? And then how do they work separately? So the first thing we studied were like kinematics. Hey, Ben.
So,
Is it common for people to like energy more than kinematics?
What's that?
Is it common for people to like energy more than kinematics?
Yeah, so kinematics only exists in introductory physics and then they completely abandon it.
It's the worst. I hate
So why do
kinematics.
we,
So because as we learn things, we need to learn them in a way that is more concrete. So you can roll a car up and down a ramp and you can plot the position and see where these equations come from. And that's easier for your brain to handle when you start developing ideas. And then we're like, now that you understand that, look at here's something that's exactly the same, only different. It's gonna be more useful for you. But you can't just jump to energy because you're like, I don't even know where any of these things came from.
okay,
Energy's so much nicer though.
it is.
I can't with kinematics every time.
So when we talk about kinematics, really we're talking about the motion of objects, right? That's the whole thing. We're talking about the motion of objects. So we have basically three type of graphs that we look at here. Right? Position, velocity, and acceleration. So if you put a ball on a ramp, it starts here, right? Moving, it's gonna go up the ramp and then it's gonna come back down the ramp, right? Now, we have a sense of what this seems like. Do we remember what the graphs look like? That's the real question. Okay? So the ball starts down here, near the bottom. Does that seem vaguely familiar?
Yeah.
Right, it does, doesn't it? And then what about the velocity graph? Okay. How do you get from the position graph to the velocity graph?
You look at
Integral.
So we're going to take the derivative moving down, the integral moving up.
Sorry, yeah.
It's fine. Listen, we're doing a thing now, right? We're doing the thing. We're trying to figure it out. We're going to look at the slope, right? So what do you notice about the slope of the red line in the beginning?
positive.
It's large and positive, which is consistent with the fact that the velocity is which way?
Forward.
How about right?
Okay.
The initial velocity is to the right, and it's a large value. As soon as you let it go, it starts to slow down on the ramp, true? All right, when it gets to its highest point, what's its speed?
0.
0. And then what happens to it?
Starts to accelerate back the other to the left.
Yeah, it speeds up in the other direction. And what I like about this, is if you look at the slope of a tangent line at the very top, slope is 0, which corresponds to the velocity 0. And I like that. That makes sense to me. What about the acceleration graph? How do we get the acceleration graph?
Take the derivative of v.
Yeah, it's the slope of the velocity graph. What do you notice about the slope of the green line?
It's negative.
It's constant and negative. Is that cool? Hiya.
Hi.
How are you?
Good, how are you?
Amazing.
What is physics club?
It's a joke.
I know, I was like, why is my name here?
So I'm here in the mornings, and there's some kids that are habitually here in the morning on Thursday morning, and we started calling it physics club just for fun. It's just for like extra help in reassessment. It's not an actual physics club. And then someone's like, well, if we call it physics club, can I put it on my college applications? I'm like, yeah, you can even say you're the president. So to go from position to velocity, you analyze the slope. To go from velocity to acceleration, you analyze the slope. Is that all right?
Yeah.
Okay. Does that seem vaguely familiar? Like, yeah, that makes sense. I remember that. Okay. So that was pretty good to me. We can also, because we understand these equations, or we understand these shapes, we actually have equations that go with them, don't we? So like the position is equal to 1/2 AT squared plus V0t plus x0. Okay? And we have all these values, or we have all these terms, like we know what this is. The A is the acceleration, t is the time, V0 is the initial velocity, and x0 is the initial position. And what shape is this? If this is a t squared, what shape does it have to be?
Parabola.
And I got that. This is a down opening parabola, so in this context, acceleration should be negative to give you a down opening parabola. And what do we have down here? Negative acceleration. True? And calculus fans, you can take calculus?
Yeah.
Is this concave up or concave down?
Bang down.
It's concave down, so you take two derivatives, what should it be? Negative value. Right?
Yeah. I mean, I'm not a fan of calculus.
Look at the sunset outside.
I'm a participant.
Sunset?
Oh, that's
You can see
sick.
it glowing against
You can
the
see all
fence
these-
line and all that.
That's cool.
It was so gross out here.
He says, I'm not exactly a fan of calculus, but I know what you're talking about, right?
I'm an unwilling participant.
Of the circus.
What about this one? What's the equation for this one?
It's a good question.
The same as that, but you just get rid of the first half.
So kind of, actually. So that's true, like, it has a certain structure. One, because it's linear, it's y equals mx plus b. Right? So the y is the v, m is the acceleration, that's the slope, x is the t, and then the b is the initial velocity value. Okay? All right, and then what about this one down here? So this is just a is equal to whatever the a value is, it's a constant. Like it? If you guys need something from me, just interrupt me and let me know. Okay. So because you have to analyze the slope, that's how you do it, like, conceptually. How do you analyze the slope mathematically? Well, we have to apply the derivative algorithm, right? We have to apply the derivative algorithm. What is the derivative algorithm?
Subtract 1 from the exponent and, or no, it's multiply by the exponent and subtract 1.
Yeah, that's exactly what it is. So to go from here to here, now, we could just do that even with these equations without numbers. Right? Think about it this way. If I do this for this first one here, I'm going to multiply the coefficient times the exponent. What's the exponent? It's 2. What's 2 times a half?
1.
It's 1. So I end up with 1 AT, and then I'm going to subtract 1, and I end up with just AT. This one, my exponent is 1. 1 times V0 is 1. Subtract 1. 1 minus 1 is 0. T to the 0 is 1. And then this is actually, don't forget, this is actually T to the 0 already. So when you multiply, that thing disappears. So applying the derivative algorithm to this position equation gives you the velocity. And if we do it again, this is t to the 1, this is t to the 1, this is t to the 0. So I'm going to multiply this by 1 and subtract, and I just get a. And if I multiply by 0, it goes away. So that's what's cool about this is, like, it makes sense in terms of the context and the mathematics, and it all works together as one thing. Something you guys have been doing that I don't know if Claire does it, because I just graded her paper yesterday, but you do the most interesting thing where when we start talking about, like, projectile motion, okay, when we're looking at the ball we know is accelerating down, constant acceleration, so these apply, but in the horizontal direction the acceleration is 0. But she still uses this equation to solve, just puts in 0 for acceleration, which is perfect. It makes perfect sense, and then you just end up with, oh, the position is equal to the velocity times the time. So as long as it's constant speed, you just have rate times time equals distance. It's interesting. So we'll see that in a second. Okay. Now, this all here, all these kinematics, you can use these equations if and only if acceleration is constant. If your acceleration is not constant, then these three equations don't work. Okay? The slope still works, and the derivative algorithm still works for you to move between them, but you can't just jump to this or jump to this if the acceleration is not constant. Because if the acceleration isn't constant, then you're going to have something wacky, like, what if your acceleration was changing with time?
Then your velocity would be quadratic and your x would be
Cubic,
exponential.
that's right.
Cubic, sorry.
So that's correct. What Jack is implying here, which is correct, is that you're noticing you have t to the 2, this is t to the 1, this one is t to the 0. Every time you take the derivative, you subtract 1. Which means that going in the other direction, you'd have to add 1 each time. So if this one starts off as linear, this would be quadratic and this would be cubic. And then this would no longer apply. So just keep that in mind. Okay? All right. Okay, so this is cool. I'm happy with this. You guys happy with this? So far so good? Feeling like you're learning something? Now, how do you go the other direction? How do you go up? Like, if I give you this graph, is there something you can find out about this graph?
Yeah.
Yeah, just use the integral.
You're going to use, that's exactly what you're going to do. You're going to look for the area. So if I want to go the other direction, okay, if I want to go the other direction, you're going to look for the area. Cool? So let's shade this area here and see what we get. If I drop this down and shade this area here, okay? What is that area going to give us?
Velocity.
So, kind of, okay? What it gives us is it gives us the acceleration is the height and the time is the width. It's just a rectangle, right?
A times t.
So that area is going to be equal to AT. Now, that's not exactly the velocity, right?
No.
See what I'm saying here? That's not exactly the velocity. So mathematically speaking, we'll do that in a second. You'd have to add a plus c if you want to take the antiderivative. We're just doing the area here. But what this tells me is this gives me, watch this. I'm going to subtract v0 from both sides. So I have v minus v0 is equal to AT. This is final minus initial. What does that tell you about the velocity? When you do final minus initial anything, what is that?
Change.
That's the change, right? So the area is the change in velocity. That's what the area tells you. It doesn't tell you the velocity value, it tells you the change in the velocity. Similarly, if I did the area of the green one, what do you think this area tells you?
Change in position.
That's exactly right. That area is the change in position. Now, what I like about this is, what do you notice about these two triangles?
They're equivalent.
They're the same size. One is above the t-axis, one is below. So one value is positive, one value is negative. So what's the total area here?
0.
It's 0.
Because the change next is 0. That's the same.
Because it starts here and it ends there. So even though it traveled some distance, what's the total change in position? It's 0. Because it went up the ramp, positive change, and then down the ramp, negative
Which is
change.
displacement, right?
That's what we call it. That is the displacement, yeah. Cool? Feel okay about that? So that's one of those things that like they want you to like have a good sense of. So this is our total understanding here. We're gonna do the mathematics here, okay? So if going down is the slope and going up is the area, if this is the derivative, this is the antiderivative, okay? So in your math classes, use the, I don't know what kind of distinction Mr. Smith makes between the antiderivative and the integral.
They're the same thing.
A lot of times we just use those two terms interchangeably. They're slightly different. An antiderivative gives you an equation. An integral has bounds, so you're going to end up with a value. Okay.
This is a not definite.
Maybe. Antiderivative algorithm, what is it?
Add 1 to the exponent.
You divide the coefficient by the new value.
Mm-hmm. That's exactly right. That's exactly right.
I mean,